Comets. Throughout history, these beautiful celestial visitors have made spectacular appearances in our skies. They have long been subject to superstition, and they've been seen as harbingers of change. But as science has advanced, we began wondering, what are they? Where did they come from? How were they formed? And what can they tell us about the origins of life in our solar system? In 2005, the Deep Impact mission sought to gain a better understanding of comets by doing something that no one had ever done before: launching a spacecraft specifically to crash into one. I'm McColgan, and you're listening to the Astrum podcast. And today we will be learning all about this incredible mission, how it fared, and what it taught us about cometary science. By 1999, 8 different spacecraft had been launched to investigate comets in our solar system, with 5 of them having flown by Halley's Comet in 1986. But beyond that, only 2 other comets had been visited: Comet Giacobini-Sinner in 1985 and Comet Griggs-Skellerup in 1992. And while some fascinating photos and dust samples had been taken as close as 200 kilometers from some of these incredible celestial bodies' comas and tails, comets still had many mysteries. What was their internal structure like? What were they made from? And how had they formed in the first place? In 1999, NASA scientists proposed a plan to hopefully answer some of these questions. It would be difficult to understand the internal structure of comets by simply looking at their surface. To know what was going on, scientists would need to dig a little deeper. Their plan was to create a crater in a comet using an impactor spacecraft, which would collide with the comet at high speeds. As they would know the mass of the impactor and the speed it was traveling at, they could calculate from the size of the impact crater valuable information about the comet. Whether its surface was a loose aggregate of dust and ice, or whether it had a hard, frozen shell, for instance. The comet they wanted to target was a short-period comet called Tempel 1, which had a nucleus of 8 kilometers long and 5 kilometers wide. Scientists weren't exactly certain what would happen when the impactor hit. Perhaps the impactor would punch straight through, like hitting a snowdrift, and not really create a crater at all. There were many theories, but scientists were eager to find out which was correct. NASA approved the project, giving it a budget of $330 million and named it Deep Impact. You might have thought that this was a reference to the 1998 Hollywood film of the same name, but apparently the names for both the project and the film had been come up with independently around the same time. Quite the remarkable coincidence if so, as Deep Impact, the film, was about scientists trying to blow up a meteor that was on a collision course with the Earth by flying a spacecraft to it carrying nuclear warheads. There certainly seemed to be some similarities to the NASA mission, especially as NASA scientists worked on the film. I don't entirely buy NASA's claim of a coincidence. Although, fortunately for the Earth, there were some differences between the film and the mission too. Tempel 1's orbit was nowhere near the Earth's, and given the size of the impactor compared to the comet, there was no chance of knocking it off its current trajectory by more than a centimeter or so. It would be more like a fly hitting the front windscreen of a large vehicle. Additionally, nukes would not be necessary to create a crater on Tempel 1, or any kind of explosives for that matter. The sheer speed and kinetic force the impactor would have when it collided with the comet's surface would be enough to create the crater, which some predicted would be roughly 100 meters across and 30 meters deep. With the mission going ahead, scientists began work on the Deep Impact spacecraft. The spacecraft was actually made with 2 parts, the payload and another larger mothership to carry it and record the result of the impact. The second section was called the flyby. It weighed 601 kilograms, was 3 meters long, and housed scientific devices, solar panels, a debris shield, and 2 powerful cameras, the high-resolution imager and the medium-resolution imager. These would take photos of the comet after the impact, as well as help with navigation. The impactor itself was smaller, only 372 kilograms, but it was still smart and housed a camera of its own. This camera, the impactor targeting sensor, would take photos of Tempel 1 right up until the moment of impact, streaming back the images it collected to its parent, Flyby, which would then relay the images to Earth. There was considerable public interest in the mission, which NASA encouraged in 2003 by getting members of the public to submit their names to be recorded on a CD, which was placed on the impactor. Roughly 625,000 names were collected in this way to be carried directly to Tempel 1's surface. On top of that, NASA timed the impact to take place on the 4th of July, American Independence Day. While this may have been because it was one day before Tempel 1's perihelion, and its proximity to the Sun may have produced clearer images, I suspect that the more likely reason for this date was that American scientists liked the idea of a large cosmic firework. Deep Impact launched on the 12th of January 2005 on a Delta II rocket. But then a problem hit. Within a day of leaving the Earth's orbit, Deep Impact's onboard computers switched itself to safe mode, which it would only do if there was a fault. Something on board was apparently overheating. This gave scientists a bit of a scare, but fortunately the cause of the problem was quickly found to be a minor programming issue. Acceptable heat tolerances had been set too low, so Deep Impact thought its thrusters were overheating, when in reality they were just fine. Engineers corrected the issue, and Deep Impact was able to properly begin its mission. The spacecraft spent the next 6 months traveling to its rendezvous point with Tempel 1. In that time, it traveled 429 million kilometers. It had to course correct twice on the journey, but this was actually impressive, as it had originally been planned for there to be 3 course corrections. One was just so precise that the other was deemed unnecessary. On the 25th of April 2005, Deep Impact caught its first glimpse of Comet Tempel 1. Of course, NASA scientists couldn't manually guide Deep Impact as there was a several-minute signal lag. Deep Impact and Tempel 1 were now roughly 130 million kilometers away from Earth, more than twice the closest distance between Earth and Mars. Deep Impact's smart onboard programming would have to guide it in for the final leg of the journey. On the 29th of June, the impactor successfully released from the flyby and positioned itself into the comet's flight path to crash into it head-on. This was done for a few reasons. First, the front of the comet was in sunlight, which would allow for better pictures to be taken. Second, it would allow a greater accumulated speed to be reached, resulting in greater kinetic force. And on the 4th of July 2005, just 1 second out from the anticipated arrival time, the impactor hit. And what a magnificent spectacle it produced. There was a tremendous release of energy, 1.96 times 10 to the power 10 joules worth, thanks to the 37,000 kilometers per hour Deep Impact's payload had been traveling at, roughly equivalent to 5 tons of TNT. What's more, dust plumed into space in a massive burst. These two factors combined to create a flash much brighter than scientists were expecting. Scientists were thrilled that they had struck so accurately. However, ironically, the success of the first part of the mission caused an unexpected negative side effect. The large dust cloud kicked up by the impact lingered, which obscured the flyby's view of the impact crater. Dust outgassed from the comet for the next 13 days, peaking 5 days in, which made it hard to see the results of this interstellar bullseye. Although it did offer some interesting insights into the internal pressures going on inside the comet. Around 5 million kilograms of water and between 10 and 25 million kilograms of dust were ejected from Tempel 1 in that time. Fortunately, scientists were able to rely on other eyes to finish up Deep Impact's mission. The collision had been observed through numerous other telescopes on or around Earth, including Hubble, Swift, and even many amateur astronomer telescopes. Furthermore, another spacecraft called Stardust that had already finished its mission was repurposed and redirected to fly past Tempel 1 and to take photos of the impact crater. It was able to do so a few years later in 2011. From the images it took, scientists were able to spot the crater and calculate that it was approximately 150 meters across, so 50% larger than they were predicting. And from this, they learned that the surface of Tempel 1 was a very fluffy material, made from more dust than was expected, and finer in substance than a powdered snowbank. The surface was incredibly porous. In fact, they were able to estimate that 75% of the comet was actually empty space, the whole thing held loosely together by gravitational forces. From analysis of the plume that had been ejected from Tempel 1 after the impact, scientists were able to identify several interesting material components, including clays, silicates, sodium, and even organic material. While not life itself, these heavily rich carbon materials may have been carried to Earth by comets in the past, providing the vital materials that make up life here. So there we have it. A recap of the deep impact mission to Tempel 1. All in all, the mission was a big success, but that was not the end for Deep Impact. Flyby was later given a new mission entitled Epoxy, or the Extrasolar Planet Observation and Deep Impact Extended Investigation, which in 2007 saw it heading off to investigate other comets and taking hundreds of thousands of photos before ultimately dropping out of contact in 2013. But by then, Deep Impact had already done significant amounts to advance our understanding of comets and our solar system. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast on the Deep Impact mission. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.